Welcome back to NET Physics series. Let's solve some of the past paper questions from the topic of heat and thermodynamics in NET. So here we have first question, question number 1, and it reads that the average translational kinetic energy per molecule of an ideal gas in terms of pressure is given by. So we want the average kinetic energy. So we know that in terms of pressure, we know that we have an equation that says that the pressure is equal to 2 by 3 n times the kinetic energy, right? The average value of the kinetic energy. Sometimes this is also known as the expectation value. Now this is not really just n, it's actually given a name n naught, while n naught is just the number of molecules per unit volume. So this just tells you, if I rearrange this expression for the kinetic energy, I get 3 by 2 p over n naught. So that's the kinetic energy, average translational kinetic energy, 3 by 2 p over n naught. So which option is that? Let's see. We need 3 by 2, right? And p up. So that's option A, right? So 3 by 2 p over n naught. So that's the average translational kinetic energy per molecule of an ideal gas. All right, so let's move on to the next question, question number 2, and that reads that if the average kinetic energy of the gas molecules become twice, then the pressure would become what? Well, average kinetic energy is becoming 2 times, right? So as we saw that the kinetic energy is given as this thing, 3 by 2 p over n naught. Now they're saying if this average kinetic energy becomes 2 times, so I'll just multiply this whole thing with 2, and so this is 2 goes with this thing, and this becomes 3p over n naught. So what happens to the pressure? We know that the pressure is just directly proportional to the kinetic energy, and so the pressure should become double as well. So we'll say that the pressure becomes 2 times. So the correct option is option C. All right, so moving on, we have the pressure of a gas is equal to. Now this is just the we have it in terms of translational kinetic energy, all of the options. So if we just remember the expression, which was that the average kinetic energy was 3 by 2 p over n naught, right? So p is equal to 2 by 3 n naught times average kinetic energy. So it means that the pressure is 2 by 3 times the average translational kinetic energy and of number of molecules per unit volume, right? Times the number of molecules per unit volume. So the first option is 2 by 3 of the translational kinetic energy of the molecules in a unit volume. This completely satisfies this definition, and hence we have correct option is option A. The rest options are very obvious why they're all wrong if you look at this expression. All right, so with that, let's move on to the next question. Question number 4. In the following VT diagram, where V stands for volume and T stands for temperature, what is the relation between P1 and P2? So you see that we have V on this axis and we have T on this axis, and where we have two lines. This is line 1, this is line 2. and line 1 is closer towards the t-axis while line 2 is closer towards the v-axis. So this line 1 has an angle which is smaller compared to the angle of the second line. So what does this tells you about pressure if this is a VT graph? So we know that if this is a VT graph, then we know that we have PV is equal to nRT, right? So this is the equation of state for an ideal gas, right? Equation of state. If these lines, I can find a relation for these lines as these lines are slopes, right? So we need V something that is of the form V over T. So clearly, if I take this thing as PV is equal to nRT, so if I take T over here, then I have PV over T is equal to nR. This means that pressure can be written as T over V times nR, which is the inverse of this slope, V over T. So even though slope 2 is higher than slope 1, but the relation is such that the slope is inverse of pressure, which means that if slope 2 is higher than slope 1, then the pressure at slope 2 would be lower than pressure at slope 1 because of this relation of inverse, which means that the correct option is option C, where P2 is smaller than P1. Of course, you can predict them, so this is wrong. They're not equal because the slopes are different, so that's obviously wrong. And P2 is greater than P1, that's wrong because we saw of this relation of this inverse thing that the slope is whatever is the inverse of P, which means that P2 is smaller than P1. Moving on to the next question, question number 5. We have which of the following expression is correct for molar volume of an ideal gas? We know that the equation of state for the ideal gas is PV is equal to nRT, right? Now, they're talking about molar volume, Vm. So if N is equal to 1 number of moles, then this means that I have PVm, which is the molar volume, equals RT. Now it's just a matter of rearranging this expression for Vm, and this becomes RT over P, which means that the molar volume is given as RT over P, and that's the correct option A. All right, so with that, let's go to 6th question. And here we have a diagram where the volume of bulb X is 2 times that of the volume of bulb Y. So we can write this as V of X is 2 times V of Y, where V is the volume. The system is filled with an ideal gas, so it's filled with an ideal gas and at a steady state. So it does not change with time. That's what steady implies. Is established with the bulb held at 200 kelvins and 400 kelvins. So we can see that this X is at 200 kelvins and here Y is at 400 kelvins. There are X moles of gas in X. How many moles of gas are in Y? Alright, so we see that the temperatures are different. We see that the volumes are different in this way. And we are asked to find the number of moles of gas in Y. So now because we are comparing the two, right, X and Y, so we can write down the equation of states for both of these. So let's write it as P for x, let's write it down for x first. So that would be px Vx equals Nx or Tx. And for y, it would be Py Vy is equal to Ny or Ty. So these x are for these P, V, and T, and even N. And similarly for y, we have P, V, N, and T. So because these are the changing variables, R is just a constant, so it's going to be the same. Now to compare these two, let's divide them. So what we can do is, let me do it over here. Px Vx is equal to Nx or Tx divided by Py Vy is equal to Ny or Ty. So we can, if we're dividing these two, we can just take this equal to as common like this, and we can divide both the sides, where r just cancels because it's the same. But remember, using some of the information, Vx is 2 times Vy. So in place of x, Vx, I can write 2 Vy divided by Py Vy and equal to Nx Tx divided by Ny Ty. Now Vy will also go away. So this means that this becomes 2 times Px divided by Py is equal to Nx. But in x, there are x moles of gas. So we'll just write small x, Tx divided by Ny Ty. Now we just want to find Ny. And we know these values for Tx, Ty, they are given as 200 kelvins and 400 kelvins, right? And Px and Py are also, well, they are not known, but there is one information that we know about these two things. Because these volumes are different, temperatures are different, which means that the pressure is really maintained at a constant value, for example, which means that Px is equal to Py, right? Again, you have to look at this equation, Pv equals nRT. If T is changing, V is changing, then P has to be maintained at a constant value. So which means that these will go away as well. And so you can see that Ny is just, if I put the values of temperatures over here as well, it's just the simple mathematics. You will get x by 4, right? Which means that the number of moles in gas Y are x by 4, which is option A. All right. So with that, let's move on to question number 7, which says that in an experiment to investigate the relationship between the volume V of a fixed mass of an ideal gas and its pressure P, a graph of PV against P is plotted. Which graph shows the correct relationship at a constant temperature? So we have an ideal gas, right? So we can use this relation PV equals nRT, and we are seeing PV against P, right? So the mass is fixed, which means the number of moles really would be same. So we see from this relation that the volume is really inversely proportional to the pressure. And if number of moles are also same, that means that PV is just some constant. So that means that the product of PV, which is this P times V, it's constant for every value of P and V, right? So whatever value I put in P and V and I multiply those things, I'll get a constant value. So if I look at these graphs, which graph is just one constant value every time for every P? It's this one, right? Because at this value of P, we have PV is this particular value. For this value of P, PV is still this particular value, and so you can see clearly at every P the value for PV is just some constant. Let's call it K. So the correct option is option B. Alright, so moving on to question 8, we see that the relationship between volume V and pressure P for a sample of gas at a given temperature is shown by the isotherm, which is marked at 1. What is an isotherm? Isotherm means that the temperature along this line is constant. So it's marked 1, and isotherm 2 would be followed by the gas if. So they're saying that why would the gas follow this isotherm? Note that on this axis we have PV, and on this axis we have P only, pressure, and here we have the product of pressure and volume. So we have that the mass of the gas is doubled. So note that we know that PV is equal to nRT. If I double the mass, then the product PV should also double. But you can clearly see that it's not doubling, it's actually coming to half of its value, the product of PV. You can see it's 2x here and it's x here, so it has decreased by half. So that's not working. The thermodynamic temperature of the gas was doubled. So again, if you double this temperature, PV should double, right? So that's not going to work. The thermodynamic temperature of a gas was halved. Now they're saying that this thing, T, if I half this thing, then I can get this thing. But note that we are talking about isotherms, which might tempt you to say that the temperature is constant, so it cannot change. But that's not the case, right? Because this still remains an isotherm. It's still maintained at a temperature, at a particular temperature, but we can change the value of the temperature, right? And we can keep that constant everywhere. So this thing makes sense. So because I can see that V is proportional to T, so if I half this thing, that would half V as well, and so the product of PV would be halved as well. For the sake of it, let's look at the last option. The mass of the gas was doubled and its thermodynamics temperature was halved, which means that if I multiply N with 2 and multiply T with half, well, that would just cancel these 2's, and then you'll still come back to this equation and nothing would happen. So this is not working. So the correct option is option C. Alright, so let's move on to the question number 9. They're saying that the absolute temperature for the ideal gas is directly proportional to the rotational kinetic energy of the gas molecules, directly proportional to the vibrational kinetic energy of the gas molecules, or directly proportional to the average translational kinetic energy of the gas molecules, or the sum of the kinetic energy of the molecules, all of the molecules. Now we know that the absolute temperature, we know that the kinetic energy is given as 3 by 2 kT. Now this is the absolute temperature, but this kinetic energy is actually the average translational kinetic energy, right? So it is how the molecules are moving translationally. It's not talking about the rotations of these molecules. So the correct option is option C, which says that it is directly proportional to the average translational kinetic energy of these gas molecules. How they're translating really, all of these molecules, how they're translating. So translation is just the linear change in displacement. All right, so next we have question 10, which says 4 gas molecules have speeds shown as this. So these are speeds given as into 10 raised to power 2 meters per second. So this means that this speed is just 1.0 into 10 raised to power 2 meters per second. This one, for example, is 7.0 into 10 raised to power 2 meters per second, and all of these are just in the same way. They're asking you the root mean square of this speed. So we calculate this root mean square as VRMS is equal to, it is simply the square root of the square of all of these velocities. So V1 squared plus V2 squared plus V3 squared, right? We have 1, 2, 3, 4 plus V4 squared divided by the total number of these speeds which we are given, or total number of gas molecules. It is 4 clearly. So we'll divide it by 4. So this is how we can calculate our root mean square speed. Now it's just a matter of putting velocities over here, and you have to remember that all of these speeds are given is in 10 raised to power 2. So if I write first one as 1.0, I'll multiply it with 10 raised to power 2 and then square it. Similarly, second one is 3.0 into 10 raised to power 2 and then square it. And then third one is 5.0 into 10 raised to power 2 and then square it. And so on, right? So you'll have finally 7.0 into 10 raised to power 2 and squared. All of this is divided by the number of gas molecules, which are 4. And this would give you an answer of 4.6 into 10 raised to power 2 meters per second. And that's the root mean square of the speed, which is option number D, right? 4.6 into 10 raised to power 2 meters per second. All right. Moving on to question 11, we have a difference of temperature 25 degrees centigrade is equivalent to the difference of what? We have 25 kelvins, 273 plus 25 kelvins, 273 minus 25 kelvins, and 45 kelvins. Now normally we know that whenever you have to go from degrees centigrade to kelvins, you do that by adding 273 to this kelvins. But note, they're asking you the difference of. So, but we know that the difference in temperature in centigrade is equal to the difference in temperature in kelvins. So, if a difference is given of temperature 25 degrees centigrade, then the difference in kelvins is going to be the same, which means that 25 degrees, which is a difference, is, let me just write this delta on top of it, is the same as 25 kelvins, if as long as these are the differences of temperature. So that's option A. Right, so let's move on to the next question. Question 12. If an ideal gas is isothermally expanded, its internal energy will what? Increase, decrease, remain the same, decrease or increase depending on the nature of the gas. Well, isothermally means, again, temperature is maintained as constant, right? So if the temperature is maintained at constant, we know that the internal energy is proportional to temperature. Now, if I am expanding a gas isothermally, which means that the temperature is constant, so that's something that you should know, that isothermal implies constant temperature, then the internal energy must remain constant as well because it's directly proportional to temperature. Hence, the correct option is remains the same, which is option C. With that, let's move on to question number 13. A gas molecule collides with the wall of the container as shown in this figure. So here we have a container. We have these two molecules of gas like this at two ends of the container. They have a same mass m and they have velocities which are moving. This one is in this direction and this is in this direction. So both masses of these gas are same. So let's suppose that I say that this is plus V and this direction is minus V. They're asking you the change in momentum. That means change in P. Now we know momentum P is defined as mass times velocity. Change in momentum is P2 minus P1. P2 is when they collide, you can see that P2 is V in this direction, right? So if this is 2, this is 1, this is V in this direction, which we told that it is a negative thing. So here we would have M times negative V minus P1, which is M and V in positive direction. So it would be M and just positive V, which becomes, let me write it over here, minus mv minus mv, and if I do this sum, it becomes minus 2mv. That's the change in momentum, which is option B, minus 2mv. All right, so moving on to question number 14, we have a gas undergoes the cycle of pressure and volume changes. So gas is going under a cycle where pressure is changing and volume is also changing at different intervals. W to X to Y to Z to W back again. And it is shown in this diagram as this, where we have pressure over here and we have volume over here, right? So the volume is, these numbers are not quite visible. This is given as into 10 raised to power of minus 3, right? And pressure is, this is just given as, let me just make it clear, it is 10 raised to power 5 pascals, right? And this is meters cube. All right, now we can see that we have this starting from W. So volume is decreasing in this direction, right? Going from 3 to 1. So it is compressing, the system is being compressed, and then volume is constant, and then you're increasing the pressure going from 2 to 3. So it's going from X to Y. Now pressure is increased. Now you're expanding it. So the volume is increasing in this direction, right? We can see this thing. It's like this. So volume increases. Now it has expanded to a certain point, Z. Then you decrease the pressure again. And so you come back to point W, like this. What is the net work done by the gas? We know that the work done is represented by the area under this rectangle, area under the figure. Now that is just a rectangle in this case, which means that the area of a rectangle would be length into width of this rectangle. Let's figure out what would be the length of the rectangle. Length is this thing, right? This distance. So it is 3 minus 1, which is 2 into this thing, 10 raised to power minus 3 meters. Let's figure out the width, which is this length, right? And it is 3 minus 2, which is again 1 into 10 raised to power 5 pascals. So that's the width. So length is 2 times 10 raised to power minus 3 meters. Width is 1 into 10 raised to power 5 pascals. Now just combine these two by finding the product of these, and multiplying these two will give you 2 into 10 raised to power 2 joules, right? Because these units of pascals and meters combined, these are the units for energy, and so these are joules. So this means that work done is 200 joules, which is option D, right? So that's the correct option. All right, so let's move on to the next and the final question of our problem set. If two systems X and Y are in thermal equilibrium, two systems X and Y, they're both at a constant temperature T, right? So T is same. So if X is heated at a constant volume, so at a fixed volume, we are heating X now, right? So if they're maintained in the thermal equilibrium, so there might be some contact between these two, and now you heat X, right? You apply some flame to this thing, and you're heating this thing, and volume remains constant. So when you heat it, you make sure that it's not changing its volume. Y is heated at a constant pressure. Now you're heating Y as well, but pressure is constant here. And here volume is constant. And again, finally maintained at a thermal equilibrium. Once the heating is done, they're still maintained at the thermal equilibrium, which means that the temperatures will be same. Then you heat Q given to the systems. Then heat Q is given to the systems. So you give some heat, you give some heat Q to this entire system of X and Y. And the internal energy stored in the system X and Y is what? So they're asking you what would be the internal energy that is stored as a result of all of this in this system of X and Y. So what happens at a constant volume for this? When volume is constant, we know work done will be zero because there is no change in volume, right? So there is no work being done. What about constant pressure? At constant pressure, even though pressure is constant, some of the heat can be converted into work, right? So heat is converted into some of the work, which means that the heat in the system Y would be greater than the heat in system X. And the internal energy in both the systems is going to be same. Why? Because they are maintained at a thermal equilibrium, right? Which means constant temperature, and if you remember, internal energy was proportional to the temperature. So wherever Q is less, Qx is less than Qy, and internal energy is same. So this is Qx is less than Qy and internal energy is same. So the correct option is option D.